Hi. Uh, Today it's kind of like a almost show and tell for the inverse Laplace transform, and the short of everything is that instead of using the table, there's actually an integral you can compute to compute the inverse Laplace transform if you're given a function which is the Laplace transform of some nice real valued function. Uh, yeah, so let's get started. So I'm going to quickly summarize the Laplace transform, not too much, just a few things. Then we're going to talk a little bit about inversion and then get into um, actually computing it with the integral, and I'll show you all that. And then before we go, I'll just uh, actually compute one by hand before going, and that'll be all, I think. Right. So the Laplace transform, this should just be a small summary. So this is the Laplace transform. So let f of t be sectionally continuous. I don't know if people still use that term. When I was reading about it, like no one actually uses it, but this is the term that they used in one of the books that I was reading. It might be a very old term, but basically this means it's like piecewise continuous, except some more. You can add like, oops, that should not have done that. You can add like holes, or you can add like jump discontinuities. And those are okay. It will still be sectionally continuous on some interval. So that's nice. Um, you might have seen these kinds of things you've done, like Fourier transforms of stuff. And then the other thing we want capital F to have is exponential order. Now, this is also not the usual way we might see it. I know a lot of times you'll see like the absolute value of f of t is less than or equal to m times e to the at, where you say, okay, this m exists, and this is true for some t greater than or equal to some like capital T. So after a certain point, the exponential is going to dominate, basically. And in this talk, I'm going to be kind of like loose about this, like just basically in like approximations when we get to like very big t, very big complex numbers, you can like say they're like almost proportional or whatever, just for bounding purposes. It's easier. So then the actual Laplace transform is this integral from 0 to infinity of e to the minus st capital F dt. And so this integral will actually converge only if you have this condition, because we want the real part of the s to be bigger, so that when like if you consider like for very big t, you can use this order approximation thing, and then we want, since this is minus st, you want the minus part to be a little bit bigger so that it shrinks fast enough. Otherwise, it blows up. That's not good. So then some cool properties. Some of the stuff is on the table, like you've seen these last for in like a table or something. So it's a linear transform. So if you apply it to some, I probably should have put like constants or something. You could pull those constants out. C1, C2, whatever. And then there are some like interesting properties involving like taking the Laplace transform of other interesting functions that make it very nice for when you're actually solving like differential equations using the Laplace transform. I am recording, right? Okay, yes. Yeah, and this thing is also just like I forgot the name. Is it Heaviside function? It's not window, but it's, yeah, I think it's Heaviside. But basically, it's like a on switch. Basically, after a certain point a, then it becomes 1, 0 otherwise. Probably shouldn't draw this line in the middle. But yeah, it just means you've shifted everything over. So it's cool stuff like that. The convolution one is really interesting too, but a lot of times this one here is nice because if you have like a differential equation with a few initial conditions, um, those actually show up when you take the Laplace transform. And so when you do all the algebra and you uh, work it into the form that you want, all those initial terms get factored in already, which is cool. Right. So inverses, right? So one issue that you might think of is like you can have like two functions whose transforms are the exact same, and the reason is because of integration, right? If you integrate a function like this, but then what if you have the same function except maybe you like delete one point and you replace it with something else? This, it will look exactly the same when you, because this is just one point. There's no difference when you're actually integrating. Like if you, it would be different if, you know, it was a completely different function altogether. But if you only have a few points where it's different and only at points, not like intervals or anything, then it's identical, which is weird, but there are ways to deal with it, but I'm not going to talk about that. There is a theorem, Lurch's theorem, that deals with all that. So yeah, and then another comment in the middle, if two continuous functions, so right here, these things, the one on the right is not continuous, but if they were both continuous and they both have the same Laplace transform, then um, they must be the same function, and that also I won't be proving. But yeah, so it is a little iffy. Okay, so now we get into like, I guess, trying to compute an inverse instead of like guessing, I guess. So we know how to go one way, know how to go the other way. Using a table, I mean, I guess, but the whole point is like I'm going to show you that the table is legit for the most part, I think. Though, pretty sure there are some, like this table is, I've seen some tables with like u of like t or whatever at every like thing, but just because if t is less than 0, then it should be 0. But those are just details. But yeah. Another thing about using a table is like, if you've already worked out whatever it is you were trying to do after taking the Laplace transform of some of both sides of some differential equation, like you're going to probably get some like nasty like p of s over q of s, maybe some some rational function like that, and hopefully your q of s, the degree of q is bigger than the degree of p. So then you're going to apply like partial fraction decomposition, which is annoying, but you know, you just got to do what you got to do, right? So there are a lot of like mistakes that come from that too, at least in my experience. I'm very bad at partial fraction decomposition, but there are some methods that make it easier, like the cover-up method, which is actually really interesting. I will talk about that maybe at the end. So yeah, so instead of using the table, I'm not saying that you shouldn't use a table. Like table is very convenient, but there is another way. So before actually like getting to the inversion integral, you can kind of like motivate it by starting from another theorem and then formally applying the Laplace transform to whatever we get. And we'll start by extending Cauchy's integral formula for a specific kind of function. So to recall, the Cauchy integral formula is this thing here, which states you've got like an analytic function f on some region like this and all of those points inside of it. Then if you wanted to compute the value of f at a point like z0 inside this region, you could integrate f of z over z minus the point over the boundary of this region, and then divide through by divide through by 2 pi I, and you'd get what you want, which is cool because then also there you could continue taking derivatives, and so now you have a way to um, get all the derivatives and everything just from doing a bunch of integrals. That's pretty cool. But we want to extend this for not just having to go around in a single loop like that. We can, for some functions, we can actually just do it over a line, and that would be that. So this is one extension. And so again, let f be analytic on like, okay, so this is, I'm going to call this a half plane. So if this is the complex plane, we want the real part of z to be greater than some gamma. So let's say gamma is here. So x, this is iy. So if gamma is this line, if the real part of z is greater than that, then it's somewhere over here. So f should be analytic in that half. And we also want f to be of this order, z to the minus k. And again, this is like before, we could just write that it's like, for large z, we have that magnitude f of z is proportional to 1 over z to the k. So for large z, this is getting smaller and smaller. And this z to the minus k, meaning this is like the dominant term, basically. Of course, it might look like a rational function, but for large z, approximation. Right, and so we want k to be bigger than 0. We want this to be shrinking. So then, if we take z naught to be some complex number in this half plane, so somewhere like over here maybe, then instead of having to integrate over some loop, we can just take the integral over this straight line, meaning the one that I already drew, this line here. You could just integrate over that line, divide through by 1 over minus 2 pi I, and you get what you want. And the reason the minus shows up is basically just because we're going like this now or something. And so the direction is reversed in that sense. Yeah, so we can prove this. I'll do this fairly quickly, I think. There's a lot of details. A lot of the things I'm going to show here are just going to be like a bunch of bounding arguments and stuff like that. All right. So we're going to, first of all, like truncate the line that I drew earlier. So instead of going all the way down to minus infinity in the negative axis and all the way to positive infinity there, we're going to stop it at this point, gamma plus I beta, and then again, gamma minus I beta. And basically, later we're going to take beta to be arbitrarily large, so this thing does go out all the way later. But for now, we make a rectangular contour like this. So we take the part that we started with, and then we add on the part going around in the box-like manner. And then this box should surround z naught. So it's basically going to be like using the Cauchy integral formula, but soon the idea is we're going to show that the integral of the blue part doesn't matter. It just vanishes anyway. So all you really needed to do is to compute the integral over the line. So we're going to do this over here. So f of z naught is equal to 1 over 2 pi, and that will distribute through because we're considering, it's like taking the integral over the whole loop and then splitting that into two integrals. And the 2 pi just sits in the front. So we have minus the integral over the line, and the minus again because we're going, instead of from bottom to top, we're going top down. And this is reflected in the bounds. This is of f of z over z minus z naught, which is over here. It can be anywhere inside the box. And then we add on the integral over s, is s being the blue part. Right. So yeah, we want to show that this thing goes away. We are going to use a bounding argument. So remember that f of z is of order z to the minus k. So for large z, if you wanted to, why does that keep happening? Okay, f of z, the magnitude of f of z is going to be bounded by 1 over z to the k for large z. And so we do that over here basically. So f of z on S is going to attain some maximum value, whatever it is, just call it M. And then we're going to add on that z to the k, which will be reflected here. And then the absolute value of z minus z naught is over here. And so we're going to factor out from this absolute value, we're going to pull out a z. So then it becomes 1 minus z naught over z. And we need to show something nice about this, because this is kind of an annoying term, but we want to show, of course, that this z naught minus z is going to go away, so that we're just left with this, which will obviously just vanish. So we'll do that now. So to show that this part is just 1 later, we're going to consider, let's draw the side of S. So if you're on S, let's say this is a point gamma 0 I or whatever. So then if you're on S, this is S going this way. This point is gamma plus, or rather, what am I doing? This point over here is gamma plus I beta. And so any point over here, 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 all of these points are going to be further than the distance between gamma and gamma plus I beta, and this beta is the length basically over here. So all of these points, even better, that's even better, because if we even take the modulus, like this beta is over here, but really, I mean, if you're measuring from the origin, you know, it's still going to be bigger than beta. So if you're on S, basically, any point on S is going to have a modulus or magnitude bigger than beta, and which is nice for bounding, because now if we take beta to be large enough, so imagine the contour S, the rectangle, just getting bigger. If we take it big enough, and you know, z naught is somewhere in the box, but if we make beta big enough so it's bigger than 2 times the absolute value of z naught, then we get some nice bounding arguments which we can use to simplify this into this. And you can show this in a variety of ways. You don't have to use the reverse. You could try just like taking this and then adding and subtracting 1. So then we can do 1 minus z naught over z plus z naught over z. And then take that as one term, take that as another, and then that will be bounded above by 1 minus z naught over z plus z naught over z. Right. I forgot where I was going with this. Right, but this is of course still equal to 1. So, so if 1 is less than or equal to this thing plus that thing, we can subtract this thing. So then 1 minus z naught over z is going to be less than or equal to 1 minus C naught over Z. Hold on. Right, but then we can use this, since Z naught over Z is always going to be less than 1/2. At most, this thing is going to be 1/2, which is, when we say that, we can drop the equality there, because we use this, we put that there, drop the equality. Why did this vanish? Okay, yes. So this thing is, again, just equal to this. That was kind of messy, but you get the point. So the actual integrand for the second integral is this thing, again. And so we bound that above using everything we just did. We get 2 times whatever that maximum value is over Z to the k plus 1. I wrote square root 2 and just because, whatever. I mean, this is just an intermediate step. We don't really need that. We already can see this earlier. But basically, yeah. So that is the bound for the integrand. And so that's just the maximum value of the integrand. For the estimation, we also need the length of the contour. And so the length of the contour is, let's draw it above again. So this is gamma, and this is beta. Right, I think I made this beta plus I beta. Same thing here, beta minus I beta. Yeah, you get the point. So this is going to be beta. This is going to be 2 beta. Wait. This is not going to be beta. Why? I probably should have inserted the image in here again, because I don't exactly remember the contour and the points. Maybe gamma minus I beta here. Oh, yeah, see, this beta minus gamma is up here. So this is beta, and then this, so the x value here is beta, and the x value here is gamma, so then this is beta minus gamma, and again, beta minus gamma. And then we have here, since this is beta, this is also beta. You do beta plus beta, and you get 2 more of these beta minus gammas, and whatever it is, it's just going to be finite, and it's going to depend on beta, but we're going to multiply the maximum value and the length. That'll be the estimation for the integral. So over here, this thing is the length. And so we multiply those together. I pulled out the beta from over here. I just factored that out. And so you get something that's just going to vanish for a very large b. So that's all. That just means that for the integral theorem extension, all you needed to do was just take the integral over the line, and that would give you what you wanted. Though you do have to negate it in the front, because the integral was going opposite of what we usually wanted it to, which is down from above instead of up from below. Yeah, so yeah, this is basically what I just said. This thing is going to go away, which is nice, and then you can put the 1 over 2 pi back in. And this is, again, what the theorem was just saying, which is nice. And this all hinged on f of z being in order z to the minus k, k greater than 0. We just needed it to shrink. That's basically all this boiled down to. So I haven't actually gotten to the inversion integral. We're going to begin doing that. So this is not actually like a motivation. It's just a cute way to see a way that the integral shows up. So I'm going to use f of s here, because that is going to be what I use for functions which are going to be the Laplace transform of some capital F of t. So if you have something that's like a transform of a function, so then we want f of s to be analytic and of order O of s to the minus k. Same thing as before. Basically, all these conditions that satisfy the integral formula extension we just showed, we can just apply it directly and say that f of s is going to be equal to this integral here. And we're going to rewrite it by just putting a limit in the front and then making clear this this part here, right? And then what we'll do is we apply the inverse Laplace transform formally. This is just kind of for fun. This is not actually, again, this is not legit. You just do it just because it's cool. But remember from your table that the Laplace transform of 1 over s minus z is just e to the zt, which is cool. But this is actually the inversion integral by itself, which is nice. Oh, that negative in the front. I also should have mentioned this negative vanished because I put it into the denominator. I swapped the z and the s. So that's why positive 1 over 2 pi I in the front. Right, so this is the integral that we take when we want to invert the Laplace transform. Cool. Right, so okay, this theorem is not going to be the best because there's a whole lot of other consequences and the conditions are kind of messy. So I guess I'll just state it here. So again, let f of x, s, we can write s as x plus iy because I'm going to use the real parts throughout the statement. Let f of s be analytic and again of this order, except for whatever reason, I have no clue why. For convergence issues, probably, but like, we'll get to it later. K has to be greater than 1, though, I mean, like, if you want her to do the inversion integral of, like, s minus z, you know, that's not this. So, like, I don't even know how, whatever it is, it's very confusing, but I'm pretty sure you could put an equal signs there, and it should work out fine, but that is just what the literature told me, and I've searched, but like, I don't know, maybe I just don't know enough to understand it. One day I will figure it out. But basically, yeah, we want f of s to be greater than the real part of some other complex number. So x naught, like x naught is just some real number over here, x naught. And then another condition that we need that I'm not going to really talk about, we need f of x, meaning if we take f on all the real values and only the real f on the real line after the point x naught, it should be real valued. Again, I'm not exactly sure why we need this. That's not really what I want to talk about. So then if you take any gamma, and this is any gamma, so I could put the gamma here, 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 it doesn't matter. Any gamma greater than x naught, then we can take the inversion integral like this over that line. So yeah, the limit as beta goes to infinity, 1 over 2 pi times the integral from gamma minus I beta, which is from the bottom, and then to get plus I beta, which is going to keep going up along that line. And then we're going to take it for this term, e to the zt times f of z. And so what you'll get is what you'd expect, a real valued function. And yeah, I'll actually show you that if you take the Laplace transform of this, I'm not actually going to show, but we'll see, because it's messy. You can apply the Laplace transform onto this inversion integral, and you can get f of s back, which is cool. There's some more consequences, like f of t is of the order that we wanted it to be, but I'm not going to show that either. There's just a lot. But the main part I'm going to show is the independence of choosing gamma. So I will show this, and I will show this. And then that too, not even like completely rigorously. So first, water break. So you want to show that if we choose gamma greater to be than whatever x naught, so if we want to choose any gamma greater than x naught, let's say we choose this gamma, let's say we choose gamma prime, we want to show that the inversion integral is the same if we take them on either of those lines at those real values. So what we'll do is we'll make a square contour or a rectangular contour that just goes around from gamma down around something like this. I probably have the arrows. Yeah, we want it to be like this. We want it to be counterclockwise on this region here. And because we said that f of s is analytic on this half plane, then the integral over any loop in that region is going to be 0. So this integral, if we integrate the inversion integral over this, or not the inversion integral, but if we take e to the zt, f of z, and we integrate that over the rectangular loop we have here, it should be 0 because it's analytic. There are no poles, nothing funky going on in there. So what do? We're going to do like again, the same bounding argument. We're going to do a contour surgery. We're going to show that the integrals over the black parts, these horizontal bits, they go away. And it's going to be very similar to how we did it before with the s, just not as much, I think. Oh, right. I see. I labeled BC over here, but I never drew that in the contour itself. It's BC. What was the other one? Whatever it is. Yeah, you get the idea. So BC being the top horizontal bit. For points on BC, you'll have that z is equal to some x plus I beta. And of course, this x is going to be like x naught over here. This is gamma. This x will be between gamma and gamma prime. So we'll put that in this interval. So it's like that. And so if you consider from the origin the magnitudes of all these points on this, they're all going to be greater than beta, because beta is just the distance from gamma or gamma prime to that horizontal bit. So that's nice for bounding, so we can just say that. And again, remember from the order condition, we have f of s and O of s to the minus k. So we're going to use that when we take the absolute value. So absolute value so if we do that, then the absolute value of the product e to zt, this is x plus iy. You probably already saw this, but like basically the iy part, that thing is just going to be spinning around in a circle. So that part doesn't really matter. It's just going to be 1 on the unit circle. So the part that does come out is the e to the xt. And so then we want to find the maximum of f of z. So then that'll just be some m, for m being some maximum value on the contour on the horizontal bit. Whatever it is, it doesn't really matter. It's just finite. And then we divide by absolute value z to the k due to this order condition. And so from above, from here, then you can replace the absolute value of z. You can bound it above by beta, which is nice. So now we have this. This is the integrand being bounded above. And so when you put this back into the integral, you got to leave this guy back in, because x is still going to vary. We write dx because you're not really going to be integrating in the vertical direction anyway. It's just going to be like a horizontal integral. So just write x. So yeah, this bound is what comes up, and so this thing over here, because we have two finite values, whatever this is going to be finite. It doesn't really matter what it is. But then, right, we take beta to be very large, and so then both horizontal bits. Oh, so it was called AD. So this is B, C, and A and D. I don't know what I was thinking when I came up with that. Whatever. But yeah, both the integrals over the horizontal bits vanish. So all you're left with is integration over the line on the left on gamma, and then integration over the line on the right over gamma prime. And so if you sum these two things up, you will get 0. So if we sum them up and get equal to 0, we can just multiply through by -1, and we can switch the direction over here. We can make this go up and this one go down. And so that's what I have reflected in this integral down at the bottom. So now see, this is starting from the gamma minus I beta, and this second one is from gamma prime from the plus. So that's top down. So, right, and so then you can take this thing, you can move to the other side. And when you do that, you negate it, you can swap the bounds. And so basically it's the same integral, just with a different gamma. And so if they're equal, then, right, this is it. You just get the equality for two different gamma. So it doesn't matter which gamma you choose as long as they're both greater than that x naught that we fixed earlier. Yeah, and of course we want to multiply by this because we did not have that earlier, but we can just put that in because they're just equal. And so these two are going to be the inversion integrals. So that's cool. So gamma doesn't matter. Right, so the next thing is actually, we'll compute the Laplace transform of the inversion integral. And so this part is basically magic, because literally we're going to be using we're going to be swapping, like if you look in the integral below, like see, this one is the one you get from applying the Laplace transform. Again, also that e to the minus st. And this thing is the actual inversion integral. This thing is f of s. Right? F of s, what? No, what am I doing? This is f of t. Yeah, because this is f of s, just with the letter changed. So we want this to be equal to f of s. But it's really weird. So first, we want to choose s so that it actually converges. So we want s, the real part of s, to be greater than whatever this real part of z was, which is gamma, because we're integrating over this this line. So if we choose real part of s to be greater than gamma, then this thing is going to dominate. Or like in the beginning when I was talking about the Laplace transform in the beginning, I said like the same thing. Right, so then actually doing it, I'm not actually doing it, because we're basically taking this, moving it down here to the right, and we're pulling out the f of z to the front, and then again this integration where you pull that to the front. All of this is just basically like, because everything converges uniformly. I don't even know what that means, because I haven't taken analysis, but basically apparently you can do all of these nice things because everything is nice and shrinks fast enough or something like that. So yeah, then you go and then actually evaluate this integral first with respect. You swap the order of integration too. So then you have this integral over here, which we can do. So that is just going to be e to the z minus s over z minus s from 0 to, since we're doing it to infinity, I'll just write infinity. We're doing it over t. So then if you remember, the real part of s is going to be real part of s is going to be bigger than the real part of z. So if you take this thing to infinity, this thing will shrink away. So then we get what? No, maybe, okay, maybe I'll write in t first. I'll just do e to the z minus s, capital T, over z minus s. And if you put in 0 minus 1 over z minus s. Yeah, and so, right, then if you take t to be very large, this thing goes to 0, so the thing vanishes. Z minus s is very big. Yeah, this is like 1 over e to the t, basically. So that thing goes away, and you get this extra minus sign. We throw that in the front, and we leave the z minus s in. So then we have one more integral to take, but it's this this messy integral over here. I should probably not crowd up the screen. But yeah, this last integral is the last thing we need to do. But if you remember, we already proved this. We did the Cauchy's integral formula extension. And so because we're integrating over this line, over gamma, from minus vertically minus infinity to infinity, and we have the minus 1 over 2 pi I, and f of z has the order condition of z to the minus k, right? All of these conditions are met. Like then it's just equal to this, which is cool. And so this is exactly what we wanted to prove, except I didn't actually prove it, but yeah, demonstration. So that's neat. So this last part is going to be about using the residue theorem to compute this, because it's just easier to use the residue theorem because it's a funny theorem. You just turn integrals into adding a few numbers and then you get your answer. It's very nice. So because f of z is like 1 over z to the k or whatever, you would expect there to be some singularities of whatever flavor, hopefully isolated, somewhere, wherever this z is 0. So usually we take our gamma to be somewhere in the positive real axis anyway. So whatever these are going to be, hopefully they're to the left. And if they're not, you can always just shift gamma, since we already showed that gamma can be whatever we want. We can always just take gamma to be as large as we want. So if you have some singularities here, here, and here, and like the origin is here, you can just put gamma over here and just integrate over that line. So all the singularities are on the left. That's what we want to do first. That's what this is. So then we get our f of s, which is going to be in the form that we want. We want it to have the order condition. We want it to be, basically we want it to be the Laplace transform of some function. Right, and I already mentioned this, but this k greater than or equal to 1, I have no idea. It should work. I just don't know how. So yeah, so this is where we get into the Bromwich integral. So if you actually try to compute this integral, it's easier to instead wrap around all the singularities to the left and then just loop around so that we can use the residue theorem. So we just add up all the singularities that were enclosed by the loop. And so you can notice I've got one floating out here, but if we take beta to be very large, we keep going like this, then eventually your loop is going to come around all the way anyway. So whatever it is, it's just going to do all of the singularities to the left. So eventually it's going to surround this. So we'll account for that too. So we have this contour here. This part, this vertical part, is going to be the part that actually corresponds to the inversion integral. And I have the contour going counterclockwise. So, right, this thing is going bottom up, which is what we want. But then we have all this extra stuff. So this is, again, the contour surgery and the bounding, and it's messy. But we want all of the integrals over these extra bits to vanish, and they do, which is nice. So we'll do that. So first, I'm going to show that the contours over the horizontal bits go away. It's very similar to what we did earlier. I hope I did this right. So yeah, so right, again, by the residue theorem, this is the vertical bit, this is the top, this is the semicircle, this is the bottom part, and so then you get 2 pi I times the sum of the residues to the left. However many there are, just sum them up. So now for the horizontal bits to vanish, AB, did I do this again where I didn't label them? Whatever, A, B, and D, E are the horizontal bits. So let me draw a sketch again of the horizontal bit, and I'll put the origin here. The origin is here. We drew the horizontal bit from the contour over which the inversion integral is usually taken. You start from the top, and you go all the way to the left until you hit the imaginary axis. So the origin will be here. And so for any of the points on this segment, if this length from the origin to the top line to this left corner here, that's just going to be beta. So beta is going to be the smallest that the absolute value of z can be. Anywhere else is just going to be a little bit bigger, which is nice for rounding. So we'll do that. So again, same game. You take the absolute value of e to the zt f of z. Again, this e to the xt pops out. Then we have to do the f of z. And again, m is just going to be the maximum value on the segment, whatever it is. It's finite. Then we use the same order condition like before. And then it'll be absolute value z to k, but then we also said that z is squared is equal to beta. So then this is again our integrand. This is almost identical, except, you know, if you notice here, we have 0 and gamma instead of the gamma and gamma prime. Again, this thing is finite, doesn't matter. So if you take beta to be very large, this thing will shrink. And you can do the same thing for dE, except, you know, maybe some minus sign shows up somewhere, doesn't really matter. So those two horizontal bits vanish, but now the more interesting part, oh dear, there are questions I did not see. Will the poles of f of z always be able to fit nicely on the left of some vertical line given the conditions? Can there not arise a case, say, where the poles are at the integers? The positive integers. You know, I'm not actually sure. If you construct a function like that, it'll be like 1 over z minus 1, z plus 2 plus 3. And that does follow. Pretty sure that would break one of the conditions. I just don't know exactly what. I'd have to look into that later. Right, it's not of the conditions. I see. Okay. All right. Back to showing that the integral over the circular arc semicircle vanishes. Now, like, yes, I could have just started from gamma and just done like a semicircle from there. But if the origin is somewhere over here, then you have this part, and those are kind of annoying to deal with. It's just easier if you instead introduce the horizontal bits and make like a weird, like, rectangle half circle contour to do this. So to deal with the circular arc, you basically use Jordan's lemma. Jordan's lemma extends the estimation lemma that we've been using, where you take the maximum of the integrand multiplied by the length. But instead of just like you would expect if a function is like 1 over z squared, that should probably converge nicely. But this Jordan's lemma will actually make it so that if you have any f of z where it behaves like even worse than 1 over z squared, so maybe like 1 over z, then that thing will also go to 0 too, even if you have this thing here. So that's why we use the Jordan's lemma here, because our f of s, I guess we've casted to f of z here, is going to be, at worst, like 1 over s or 1 over z. And so we can use this lemma. I will actually prove it in a little bit. This is not actually Jordan's lemma. Jordan's lemma deals, I think, with semicircles and the top and the bottom, but never this way. So like this and this, but not like this and this. But the proofs are similar enough, so I just recreated the same bounding argument. So yeah, so this thing is just saying that the points in the contour are like this, and then again g of z being of this order, so just shrinking, not just 1 over z squared, but just shrinking in general. Then you can apply this. Right, so then if you take the integral over this circular arc of this thing, then you get 0, and a has to be real and positive, because in the integration you don't want extra negatives coming in. I think that would mess it up. But yeah, if we take a equals 1 and then g is equal to f, then we basically get what we want. That was our case in the integral that we're working on. So this is just a little bit more general, just for fun. Right, so again, the bounding game. So we're integrating over this semicircle like this. So we parameterize first. So this is the radius r. And so the angle is going to be between pi over 2, which is at the top, and then 3 pi over 2 at the bottom. And then we'll take the absolute value of the integrand with all of this said. So if I do z equals this, you have to also remember the dz part is I r e to the I phi. So that thing comes to here, and there's a d phi in there somewhere, yeah. So then this thing goes to here, this thing goes to there. That's just parameterization. And then, then, so over here, we have e to the at r, and then we get see the e to the I phi, we get cosine plus I sine phi. And so the reason we can get rid of this is because it doesn't really matter what is outside of the I. Whatever it is, it's just going to, because this is e to the stuff times I, whatever it is, it's just going to be on the unit circle, so that's just going to go to 1. So this part doesn't matter. We can leave the cosine, because that's the real part. That thing might change. Even though it oscillates, it's definitely going to have some impact. So then we're left with this from that first one. And then from the order condition, this g will be around 1 over, what was it, z to the k, absolute value z to the k, if we bounded it. But then z is equal to r e to the I. So then, the r is going to be the length. So then we just replace the absolute z with the r. And so then this is the same thing. You just get the r, and then I is just 1. So you have this, And so now we have this. Now you might be worried, like, we have r to the k minus 1, but I already said that k was like supposed to be great. What if k is some like number between 0 and 1? You get this minus 1. In future step, we'll have another r pop out, which will fix this. So this is the first step in bounding. So then we'll rewrite some more. So then we shift to the theta variable because we have this 3 pi over 2 and this pi over 2 that's kind of yucky, and we actually kind of need it because we're going to do another cheeky argument after this. So when we shift from phi to theta, right, theta will be phi minus pi, so this pi over 2 goes to minus pi over 2, this 3 pi over 2 goes to pi over 2, and then this cosine phi, because then you replace it with theta plus phi, because of the periodicity, the pi makes it shifted so that you get a minus sign in the front. So now we have this, which is cool. We love to see minus signs in our exponentials. So then another thing we like to do, we'll do some symmetry because the e to the stuff times cosine. So if your cosine looks like this, oops, right? Okay. Yeah, then you take the exponential of e to the minus stuff. I think I graphed on Desmos one time, but like to freehand, it might look like this or something. It'll go up and down, or something like that. It'll still be periodic. So, and so it'll have some symmetry over the y-axis. So then you can just integrate from 0 to pi over 2 and then double it. But this was actually really important. So now we can actually just focus on 0 to pi over 2. We don't have to do anything else. So now that we've focused our interval to 0 to pi over 2, what we want to do is we want to continue bounding this from above. Like this is kind of yucky. We don't really have a way to integrate this immediately, but there's an easier way if we just bound it above. So e to the stuff times minus cosine theta is going to be less than or equal to e to the more stuff, the same stuff, times we want some h of theta. So we want h of theta to be less than cosine theta because when you have the minus signs in the exponential, when you take 1 over, it's going to end up being bigger. So I'm just going to let this be this, and I'll draw the picture for this. So this is 0, this is pi over 2. This is the cosine. Cosine is going to go like that. But then this h of theta, this is a theta axis. And then the h is going to be start at 1. And then you're going down all the way to the x-intercept, which is going to be this. So then this linear function, basically, this linear function will always be less than or equal to. Great. So now we actually have a way to bound above, which is cool. We have this. And we can actually integrate this. Once we write it in this form on the right, this is nice. This thing just comes out. And then this thing, we know how to integrate because it's just a constant times the theta. So we put that back into the bounding. So right, I pulled out this extra exponential. So now all we have to do is deal with this, and you just do it directly. You just integrate it and you'll get this. And so then you multiply everything through. This e to the minus atr, this will cancel with this, and you'll get the minus 1 times this, which will come down here. All right, so I multiplied that through. I pulled this pi back up to the top. I canceled this 2 with this 2. All of this simplification to get this bound. And so also notice that I said that there was going to be another r. Yes, yeah. in the usual proof for the Jordan lemma, you will do this for sine, and sine is concave, and so you can do, yeah, exactly. The cosine variant is the same, basically. Yep. And so, right, this extra r, I said, was going to come out, and it did, and that's nice. So now k can be just greater than 0. It can be 0 between 0 and 1. So that's fine. So indeed, if you take r to be very big, then this thing vanishes. The integral over the semicircular arc just goes away. So that's cool. So now we've actually shown, so we did this part, and we've also done this part. So all three of those extra bits, the integrals over those go away if you take, I suppose beta r, I mean r is going to be equal to beta, but whatever. If you take it just big enough, then all the extra stuff goes away, and all you're left with is just this inversion integral, or at least part of it. We still need to, in front of everything, there should be like a -1 over 2 pi I. But we'll get to that. That comes from after we do this. Like right now, this last part is just going to be the integral from gamma minus I beta and gamma plus I beta is zt f of z dz. We will get the 1 over 2 pi from the residue theorem, right? So all of these other three go away. Oops, maybe I shouldn't delete that. Right, so then the results of our operation, we're left with this, and then usually, like I put the 2 pi I over here. Usually you get 2 pi I times the sum of the residues, but you pull that to the left side. So now this is the inversion integral. And then all you have here now are just the sums of the residues at all of the isolated singularities to the left. That's really convenient. Yeah, I mean that's it. I don't really have any more theory to say this was it. After this, we'll do the cute example, and then I'll call it quits. Right, a cute example. We are going to compute the inverse transform 1 over s squared plus 1. Right, so we'll do this, and so you can draw the contour. Doesn't matter what gamma we pick, just make it big enough. And then we take our horizontal bits, and then we'll take this. And so the singularities of this, we get a plus or minus I, so it'll be around here. Right, and from before, we don't actually need to compute all these extra bits, since they just vanish if we take the radius or the overall just size of the contour to be very big. So all you have to do is sum up the residues. And I like to do this in a, like with a trick, I guess. I don't know if this is a trick. I'm not sure who taught me, but this is basically the cover-up method, but for residues. So we want to compute from gamma minus I beta gamma plus I beta of e to the zt, and then this will be 1 over z squared plus 1 dz. Right, so now we gotta compute the two residues at these two. So the way I like to do it is, I'll write the pole, so z, let's erase it, z equals I. So then first I'll write the, integrand as e to the zt over z plus I, z minus I. And so at z equals I, this part is the problem part. So then what we'll do is we'll write e to the zt over z plus I, all of that over z minus I. This is inspired from the Cauchy integral formula. So then this is basically like covering up. You cover up the z minus I, and you evaluate the stuff on the top at z equals I. And that'll just be your residue. So then you get e to the it over 2I. So that's one. Well, now we need to do the other one. Z equals minus I. Then we'll get e to the zt. Now the problem spot is different, so we'll put z minus I in here, and then we'll do z plus I at the bottom. So then if we evaluate the stuff at the top at z equals minus I, then we get e to the minus it over minus 2I. And then we're going to sum these up. We sum those up. So I'll pull out the 1 over 2I, and then we'll get e to the it minus e to the minus it. And for those who've seen this before, this is immediately just the, right, this is just the limit, yeah, of the z minus I times, yeah, that's the same thing. And so, yeah, immediately this thing, you could write out the real and imaginary parts, and you'll get the cosines cancel, and you'll get like 2I sine t over 2I, and that's just equal to sine t. So yeah, that was pretty cute, I think. Yeah, that's all I had to say. That's the talk. Thank you for coming. I had an extra slide in case I had comments. I guess the only comment I had was, talking about where I learned this stuff. So the book that I was reading a lot to figure out this stuff initially, it's called Operational Mathematics by Ruel Vance Churchill. And it was, the version that I have is very old. I think it was like published in 1960 or whatever. But I don't really know where to find like the stuff that's like at a kind of accessible level. There's another textbook, I think I don't know if I'm spelling that right, but that's like one of the books that Churchill frequently says to take a look at for the details. But I assume it's going to be some crazy book that needs like a lot of background, which I don't have. But yeah, that's like this book is where I mostly learned this thing. It's a nice book. I should probably try to read some of the other chapters later on. But yeah, thank you for showing up. I'm gonna stop recording.